Okay, fine. Good evening, everyone. As per my time zone and all, I would like to thank the organizing committee for providing me this opportunity to present my research work in a nice international platform. The presentation which I'm going to elaborate here is emphasized on regioselective and atom economical metal-free C5 chalcogenation of 8-aminoquinoline under mild condition. So this is mostly related to the heteroatomic heterocyclic compounds which has been functionalized in a regioselective manner in like ambient temperature and ambient reaction conditions. So as we can visualize in our daily life and in our surroundings that the quinoline based compounds can be seen as a prevalent scaffold existing in many drugs as well as the bioactive compounds. Let's take the examples of primaquine, tafenoquine, which are well-known anti-malarials, which has been already approved as drug, as well as we can see this core structure in many other bioactive compounds, such as lenvatinib, leotonins, which are actually functioning as antivirals also. So accordingly, we can find a lot of literature methods are there towards the synthesis and functionalization of quinoline derivatives. Related to this kind of research, which has interested or which has grown interest in scientific community, we were mostly targeting this site selective functionalization of quinoline derivatives. So previously, our group has already explored the functionalization and annulation and different kind of coupling reactions with heteroaromatic compounds, mainly the indoles and pyrols. And we have published some papers related to that, but that was mostly with the transition metal catalyst, which we used like palladium and copper, which selectively, site selectively annualized the heterocyclic compounds systems which we have developed. So here, after that, we thought of doing the similar kind of functionalization without the aid of transition metals, so that we can develop a greener or environmentally benign conditions for the functionalization of quinolines. So accordingly, when we surveyed the literature, we found previous reports was mainly based on whichever was the metal-free conditions were based on the functionalization or C5 selective functionalization of 8-aminoquinolines that were protected, that were actually functionalized in the amine groups. So that gave the fluoro functionalized as well as the like amino functionalized products from the previous methods which have been developed till now. So next, when we thought of specifically the chalcogenation reaction in 8-aminoquinolines from the previous literature, what we found that the C5 chalcogenation of 8-aminoquinolines are not reported at all, and whatever has been reported was with the use of transition metal catalysts, and in addition, they have protected the amino group with different functionalities. So checking this kind of previous literatures, we came to a conclusion that a process development is required in the field of 5 substitution of 8-aminoquinoline without a protection, which can further be functionalized, further be manipulated for functionalization with this unprotected amino group. Now, what previous report was there, I will specially emphasize on this copper catalyzed reaction where the chalcogenation has taken place in the C5 position of 8-amidoquinolines. But here they have used copper catalyst as well as they have used the elevated temperature. So both these factors what we targeted was both these factors. We can remove these factors and make it an environmentally benign condition to implement on. So the objective was met when we did the reaction under the transition metal precondition with iodine as catalyst. So what points we were able to like justify, and the advantage which actually came out from this methodology was it's kind of atom economical reaction conditions that we develop that doesn't actually give the side products to interfere or towards the product development. Secondly, it was the transition metal-free reaction condition. Then it was at room temperature, which was again an advantage if we consider the reaction condition the ambient condition, which it appeared to be for our standardized reaction. Then the C5 regioselectivity was almost complete. So although we have isolated the 5,7 disubstituted, but we were able to standardize and optimize the reaction so that we can get only site selective C5 product. So that was the other advantage. Next was the unprotected amine group was able to be utilized for further derivatization towards different products. The reaction yielded approximately 85 to 90% yield of the product. Again, it was scalable to the gram scale without lessening of the or without reduction of the product in a significant amount. So the reaction conditions which came out of the optimization reaction was that iodine was used in 10 mole percent along with 0.5 equivalent of tert butyl hydroperoxide in acetonitrile as solvent and room temperature. So that selectively produced the C5 chalcogenated 8 aminoquinolines in excellent yields. During the optimization of product, we found that different kind of observations were there by altering the iodine amount that was used in catalytic amount as well as the oxidant amount. Then the solvent was altered, time and the temperature was also standardized during the reaction condition. When we started it with the DMSO as oxidant and 30% of iodine as the catalyst in neat, then we obtained only 50% of the desired C5 selective product and 8% of disubstituted undesired product. Accordingly, we changed the conditions with solvent change from DCE, DCM that gave us more of disubstituted product instead of improvement of the desired product. Then afterwards, we tried to change the oxidant from DMSO, DMF to AIBN, and then H2O2, that is hydrogen peroxide, actually led to the decomposition, complete decomposition of the product. Therefore, we were unable to isolate any products, neither the C5 chalcogenated product nor the dye substituted product. Finally, when we arrived with the oxidant as tert butyl hydroperoxide, it increase the yield of our desired product to 70%. And again, the reduction of the iodine amount to 10 mole percent gave us the desired reaction condition with 85% yield of desired 3A products, that is the C5 chalcogenated product, and the disubstituted was obtained in trace amount. In some cases, it was totally absent. This was the best condition which we actually developed. Further increase or decrease in iodine and the oxidant led to decrease in the desired product. Now, these are all the examples which we did with altering the substitutions of dichalcogenides as well as the aminoquinolines also, where we can see that the electron withdrawing groups in dichalcogenated substrates led to decrease in the product of the reaction. So where it actually hampers the yield was finally got into when we established the reaction mechanism. So almost around 24 substrates were tried and tested, and they were obtained in moderate to excellent yield. Next, this methodology was implemented and the application was observed in the derivatization of N-Bock protected primaquine. As I have already shown in my first slide, that primaquine is kind of anti-malarial, already established as a drug in market. So when we just took that drug out and protected the N terminal and applied our methodology, we obtained the C5 selective chalcogenated product in 50% and 90% yield with selenium and sulfur analogs. So this proved as a nice process to be applicable to derivatization of drug molecules also. Now, controlled experiment was done to prove the mechanism of the reaction, whether it is an ionic reaction or it is a radical reaction pathway that's followed. So when we did this reaction with the TEMPO and BHT, which are the well-known radical quencher, we found that there was no significant decrease in the yield of the product, which partially indicates that the reaction is not going through the radical pathway. Otherwise, the yield could have been decreased significantly, and we might have obtained the side product, which sometimes is visible through mass spectroscopy. So that didn't happen, and we analyzed that an ionic mechanistic pathway is there behind the reaction. So next reaction which was there was the protected amino group. As I've already discussed that the previous groups, what they have done was with the protected amino group, and they have functionalized the C5 position. Here, when we tried the same thing, it was seen that there was no reaction and only the starting material was recovered that was intact in the reaction mixture. Finally, when we did the reaction with thiol instead of the disulfide compounds, then we again were able to get the desired C5 chalcogenated product in 45%. Although the yield was low, but it indicates that the thiol compound can be used as the substrate instead of the dichalcogenated substrate. So then we tried to go for the mechanistic interpretation of the reaction, which actually tells that the iodine which is used as the catalyst might have uh, gone through the reaction and it might have helped to cleave the SS and SE bond which are present in dichalcogenides, and as a result the iodide compound might have formed as an initial intermediate, which then adds or which then undergoes the electrophilic reaction with this amino quinoline compound to produce the intermediate B. Then it undergoes the loss of HI and release of the product, the desired product, that is the C5 chalcogenated product 3. The HI then gets oxidized again with the help of third butyl hydroperoxide. Third butyl hydroperoxide itself gets reduced to third butanol. So it's kind of the redox reaction which is going on with oxidation and reduction at the same time, and the iodine is regenerated. That's why it is used as catalyst in the reaction with 10 mole % concentration. Now, these all reaction mechanisms were suggested with the help of the controlled reaction done with TEMPO, BHT, as well as the other controlled reaction which I have already shown in the previous slide. Finally, what we did was the kinetic isotope effect experiment to show whether the CH bond breaking is occurring in the rate determining step or not. So when we like started with the deuterated compound, dideuteriated compound of aminoquinoline along with the similar equivalent of undeuteriated compound, then we did the same reaction with iodine, PBHP, and acetonitrile. What we have seen is there is the production of the of 50% of the deuterated and 50% of the hydrogen containing product, which was evident from the NMR spectra. We got the rate determining step. We got to the conclusion that the rate determining step doesn't have this CH breaking in it or CH cleavage in it, since we are getting the KH by KD ratio of 1. So that also is supporting the kind of like reaction mechanism which we have suggested through different controlled experiments. So from this we can conclude that we have developed an atom economical metal free CsP2H functionalization of 8 aminoquinolines at ambient and mild reaction conditions, and this actually enhances or this actually ensures the exclusive regioselectivity for C5 chalcogenated products. The protocol itself is an eco-friendly and a simplified synthesis method, and diversely functionalized substrates have been used as a kind of for the generalization of the reaction and formation of product from moderate, getting the moderate to excellent yield. Control experiments have been done, which indicates that the reaction possibly proceeds through the ionic mechanism instead of a radical mechanism at the room temperature. Next, the reaction conditions are scalable because we have done it till 1 gram and without getting a reduction in the yield of the product. So it's kind of the scalable reaction, we can say. The generalized method was successfully implemented for late stage diversification of pharmaceutically important primaquine analog, where we have shown from 50 to 90% yield of the derivatized drug product. Thank you, and I will like expect questions from the audience. Thanks to everyone.